And welcome to a new video about controller realization. This is our example number 6. In this example I would like to discuss the realization of a lag lead controller. So we'll look at the calculations again step by step to make this specific circuit and also verify our calculations using simulations in SPICE. So let's look at our example. We have the following design. We would like to design a physical electric circuit for a given lag lead controller transfer function, which is shown here. So GLL, or lag lead, is given by this transfer function. You can see in this transfer function two zeros and two poles. The poles are at the minus 0.01 and at minus 20, and the zeros are at minus 0.2 and minus 1. The lag pole and the lag 0 is actually given by this transfer function, which is the s plus 0.2 over s plus 0.01, and the the lead and the lead 0 and the lead pole are given by the s plus 1 over s plus 20. So the product of these two, lag and the lead, will give you lag lead controller. The lag is specifically useful for reduction of the steady state error, and the lead is for speeding up the process response and also giving some less overshoot. So together we can get the specifications we want using this lag lead controller. And it is a passive realization because the gain here is once you don't have the amplifier. So let's look at our solutions. The candidate for this transfer function or the realization for this circuit is given by this circuit. So you can see there's a combination of the lag and the lead circuits we have discussed so far in the examples number 4 and 5 in the previous videos. You see the part here, the parallel combination, and you see also the series combination of the RC circuit. So together you can make now the lag lead control using these two combinations. So let's then make the transfer function of the circuit again, and we'll look at the voltage divider rule by saying the VO over VI. That is actually what we want. Now before we move on, let's also designate the impedances, because this parallel combination of R1 and C1 can be given by the impedance ZA, and the series combination of the R2 and the C2 will be then the ZB. So I just designate that like that. Then we can say the following. I can now see that there are two impedances, and then I can say the voltage across the ZB divided by the voltage across the ZA and ZB is actually my voltage gain in this circuit. So V over VI. You can see that the VO and the VI are in capital letters. That means we work in the frequency domain. So what is ZA and what is ZB? Now we already said that the ZA is in parallel combination of R1 and C1. That means it is the XC1, which is the reactance of the capacitor C1. Now that's given by this in a very short notation. When you expand this, you get this expression because the capacitor can be given in the Laplace domain as 1 over SC1. And when you work it out, you can say R1 times the reactance of the capacitors divided by the summation of these two. And then when you work it further out, you get this one. So this is the nice expression for the ZA. So you multiply the numerator and the denominator by SC1. Alright, that's the first step. We're now going to the ZB in a similar form. Now we have now R2 and the capacitor reactance C2. That's shown here and already given in the Laplace representation. And when you combine them, you get this expression. So we get now R2 times C2 plus, R2 times C2S plus 1 over SC2. Now we have now two expressions for the impedances. Now we can place this in this equation for the H, which is then the transfer function of the circuit. Now the red one over the blue one plus the red one. So that's actually just designated here. We can further simplify this by multiplying the numerator and denominator by SC2. So you can see that as the next step. So this will then, you will lose this in the denominator, in the numerator, and also this one in the denominator. And this will get then C2 times S in its coefficient here. Okay. Now we move on, and then we'll also want to get rid of this fraction with this R1 times C1S plus 1. That's the next step. You can see that here. So then you multiply the numerator by this term, which is R1 times C1S plus 1. This will be also multiplied by the same coefficient, and this will then only be R1 times C2S. That's shown here. Now we can further multiply this out and also simplify this such that we get this transfer function of h similar or closely related in that format to the given lag lead controller transfer function. So I will move on and then do the next steps. The following, I will take out R2 times C2 out from this first parentheses and also do the R1 and C1 out. So the next step is this one. So I will leave the denominator as it is. Actually, I mean this part. So the first part here is taking out R2 times C2 and also R1 times C1. But symbol is the exact same here because this coefficient here, the term, is the exact same as the term in the numerator. So you can see what's happening. So now we can divide out this term because R2 times C2 and R1 times C1, that's the product of 4 elements, is also shown here. But you have it also here, but partially. So when you divide out R1 times C2 over the product of these 4, you will get this expression. So it is now, you lose this, you lose this, you lose this, you lose this. You get the parentheses. But you have, of course, here 1 over R2 times C1 because that's the part of what is left by dividing out the coefficients. Now, when you move on, you can also work out these parentheses that's shown here. So you can see the s squared plus etc. Because this working out the parentheses, you will get this expression. Now, when you work it further out, you can now collect the s terms also because there's an s term here. Now, if you bring it here in here, you get now the final result, which is shown here as the transfer function. This is not exactly the representation given by the lag lead controller. So there is a denominator which is in a product and we have it as a polynomial, but we'll work it out shortly and compare the result closely to the given expressions here. So let's bring it together. Now this is then the transfer function we have of the circuit, and this is the circuit itself on the left side, and this is the transfer function of the lag lead controller was given. Now I have this already giving some colors, the blue and the red and the green and the pink colors for designating the location or the parameters. And this is the transfer function we have from this lag lead controller. If I now work out the denominator here and then make a polynomial, I can then do s times s squared, plus s times 20, and then plus 0.01 times s, and then plus 0.01 times 20. Then the result will be this one. And if I now compare this to the given transfer function of the circuit, then you recognize directly which one is the parameters. So you can see 1 over the R1, C1 is this one, etc. So let's then compare the results and then H and the GLL. So 1 over R1 times C1 is already 0.2, that's shown. The next one is the 1 is equal to this, the red one. And the green one here, the 20.01, is that complete expression in here, that's shown here. And we have also the fourth one, so 0.2 is equal to this expression, the product. Now it looks like that we have 4 equations, so we can say now, let's then use this and then also get 4 unique values for the resistors and the capacitors, because we have 4 unknowns. And we have 4 equations. It seems like we have 4 equations, but let's also be careful with that one, because when I look at this equation in pink, it's actually a product of this, the blue, and the red one. Because if I multiply this and that one, I will get exactly this one. So it is dependent. It is not actually an independent equation. I cannot say that for this one, for example. Also, I cannot say that from this one. So I cannot make this out of these 2, but I can make this, the pink one, out of these 2 equations. So we can say this is not a unique equation. So we can say this is not what we can use as the design equation at the moment. So these are the 3 equations which are unique, and we can say again that we have 4 unknowns still, but again just 3 equations. So we need to select one of the parameters. And let's again select one of the capacitors. In this case, it's just C1 or C, doesn't matter. So I just select, in this case, C1, I will make it 1 microfarad. Okay. When I select this, then can I say then the blue one will give me then the value of the R1. So R1 is then equal to 1 over the 0.2 times C1. Since C1 is selected, we can just substitute the values, so you get the 5 megohm. So that's done. Now, in order to get the other values, because we also need the R2 and the C2, we can use first this equation, because I don't know R2 and also I don't know C2, so this equation is a little bit, you need to wait for that. Let's go to the equation in green. We can say this 20.01 is this equation, but this here, 1 over R2 C2, is actually the blue one. That's actually also given here, the blue. And the second term is actually the red one. And I can use these values because they are given 0.2 and 1. So let's given here, let's then do that. And then now further simplify this. So you get here 1.2, subtract from this part, you get 18.81 is equal to 1 over R2 times C2. Now when you work it out for the R2 here, since the C1 is known and also the value here, then we can now work it out using the selected value for C1. And that will give us 53.163 kilo ohms. So that's the resistor value for R2. Now, since we know the R2, we can now use this red equation. Now, moving on, we can say the C2 is equal to 1 over R2. That's the easy equation here. And when you substitute this value we just determined for the resistor R2, you will get 18.81 microfarads. So we have now our capacitor value, also C2. So we have now everything. So let's collect them. And this is the result. C1, C2, R1, and R2. Okay. Let's bring up the simulation results because we would like to check our calculations for this specific situation using the frequency response. This is the Bode plot. You can see the gain here and the frequency. And also the phase here and also the frequency. So you can see the gain and the phase response. This is the circuit. You can see the circuit here. So we have the R1, C1, R2, and the C2. Okay. What do we see here? Let's begin with the low frequency part. The low frequency gain here is 0 dB or 1. Why? Because the low frequency gain is actually given by substituting here as a 0. That means 0.2 times 1 over 0.01 times 20. And that is actually 0.2 over 0.2. That is indeed 1. So, and if you now do also the calculation using the log equation, so to get you to the dBs, you get indeed 0 dB. In a similar form, you can look at the high frequency gain. That's the extreme part of the part. So it means actually you look at the situation where this S goes to infinity. So you can actually look at it like this. And that is also 1 because if this is infinite, so you get infinite times infinite over infinite times infinite. So you get actually again 1, so in the infinite frequencies. So again you get 0 dB. So 0 dB at the beginning and 0 dB at very high frequencies. And in between it happens something because it gets now a very, let's say, small value as a gain. That's the characteristic of a lag lead controller. It has some, let's say, a minimum value, sort of a band stop filter. But let's first look at the pole and the zero frequencies. The lag pole frequency is here. You can see that it is 1.596 millihertz, and converted to the radians, it is 0.01 radians per second, which is this one. So that is exactly correct. You can also see the lead pole, because that is the farther pole, which is at 20 radians per second, which is also correct because it is 3.182 hertz. But the other two, which is then the 0.2 and 1, so the lag 0 and the lag and the lead 0, these are a little bit off as the calculated values. Looking at the calculated values, because this is the lag 0 and it is given almost at 0.15 and we want 0.2. So you can see the difference here because it must be this. We have this. And the other one is it must be 1, but we have almost 1.35. This is here. So we should have 1. So you see actually the two locations here, the lag 0 and also the lead 0 are actually splitting. So it's actually moving away when they are close to each other. So this, because these are not really far away, because the ratio between this and that one is approximately 5, it is not really that far away. So if you have a situation like this, there will be definitely a huge, let's say, interaction between these two zeros. If you want this effect minimum or very small, then you need to place these zeros, also the poles, actually very far away. That's the reason for having this situation. So if you want a very accurate result, you can use other algorithms like, let's say, what we use in the filter algorithms, the Geffe algorithm. Again, you can still fine-tune and get the results. So the lag pole and the lead pole are very close, but the lag 0 and the lead 0 are somewhat off according to the required calculations, and we still have a nice shape. You can also see that from the face, it started at 0 degrees and then jumps actually down to a very negative value. It's minus 62.5 degrees approximately, and then jumps again at 0 degrees, and then jumps to the maximum value, exact same value, but then a plus, and then reaches again the 0 degrees. So you can see it is also doing a similar thing as the gain response. Alright guys, this is our example number 6 about the lag lead controller realization using a physical electric circuit. We have seen how we can determine the coefficients or the values for our capacitors and resistors in this circuit, and also verified this in this simulation using the frequency response. And we see also that some of the values are off according to the required transfer function. And also the reason for that is because they are very close to each other. If you have any questions, comments about this example, please let me know and I will try to answer them as soon as possible. See you next time in another video. Take care.